In today's lesson, we will be learning how to solve the system of linear equations via the use of the determinants. This method is known as Cramer's rule. Finding the determinants, the diagonals method. So in this method, the first two columns are mirrored to the right of the third column. Right, so we're just going to repeat, mirror. So the determinants is equal to the sum of the products along the diagonals from the top left to the bottom right minus the sum of the products along the diagonals from the bottom left to the top right. So the leading diagonals are so think of it as the formation of the letter V. You have to come down, right, before you go up. And it's the sum of the products. So the determinant can be found by using this formula here, and it's the sum of the products of the leading diagonal. So A1, B2, C3 plus the product of B1, C2, A3 plus the product of C1, A2 and B3, right, minus the sum of the products of the non-leading diagonals. So it's A3, B2, C1, B3, C2, A1 plus C3, A2, B1, right? And you would want to work out the brackets first, each individual bracket. Example 1. So we have our matrix here, and we're going to find the determinant. So the first step, you mirror the first two columns, which is that. So 2, 1, 0, 1, 3, 1. I want to find the determinant. So the determinant is this will be equal to 12 minus 2, which is 10, minus 8 plus 2, which is 10. So the determinant is found to be 0. When the determinant is 0, this means that the matrix is singular and it cannot be solved. Alright, so we're officially going to start Cramer's rule now. So for this, we are given 3 equations, 1, 2, 3. So what we have to do is, we're looking at these equations, we're going to rewrite it in matrix form. So we're going to open our bracket, A1, B1, C1, A2, B2, C2, A3, B3, C3, right? X, Y, and Z. Then the constants D1, D2, D3. Now, when we're writing this, you know normal multiplications is rows by columns. So if you multiply it out, you will get the same thing originally. Once Cramer's rule is applied, these formulas will be used to find x, y, and z. dx over d, dy over d, dz over d. D is the normal determinant, dx is the determinant of x, dy is the determinant of y, dz is the determinant of z. It is always advised to calculate d first. If d is found to be 0, right, the system of equations cannot be solved due to the matrix being singular. Alright, so the question is now how to find dx, dy, dz, right? So from the equation here, you remember we said to work out d first. D is found now by the normal procedure, the determinants, the product of the leading diagonals minus the product of the non-leading diagonals, right? So to find dx, the variables of the x column, which is the A column, right, are replaced with the variables of the constants, which is the D column. So in this case, all the A values switch to the D values, right? The B's and the C's remain normal. So after you replace that, you want to mirror the first two columns, right? Which is the D and the B. Same procedure, right? And you're going to find the determinant by the product of the leading diagonals minus the product of the non-leading diagonals. Similar for dy is the same where the variables of the y column are replaced with the variables of the constant. So all the b's switch to these, and we just mirror the first two columns, and you solve the determinant as normal. Same with the z situation, right? You replace the z column with the constants, which is the d's, and you mirror the first two. So from here, you would substitute the values of the determinants for dx, dy, dz, right? Where x is equal to dx on d. D will be found first. And once that is done, the value for x, y, and z will be found. So we have this example here. So you're going to follow the same steps. First step, put it in matrix form. 1 minus 2, 4, 1 minus 4, 3, 1, 3 minus 2, right? X, y, and z is equal to 3 minus 5, 6. So we're going to find the determinant, D, right? So we're going to rewrite the matrix first. And what we want to do is we want to mirror the first two columns. 1, 1, 1, minus 2. Right? So to find the determinant, we know is the sum of the products of the leading diagonals minus the sum of the products of the non-leading diagonals. Right? So 8 minus 6 is 2. 2 plus 12 is 14. Minus 16 plus 9 plus 4 is minus 3. And if you notice, we have the occurrence of two minus signs here, which makes it a positive sign. So it's 14 plus 3. And the determinant, which is d, is equal to 17. So we're going to find dx. Right? So in order to find dx, we have to replace the column with the x values with the constants. So 3 minus 5, 6. Right? We put back the rest of the columns normal. And we mirror the first two columns you see over here. And we know the determinants is equal to the sum of the products of the leading diagonals minus the sum of the products of the non-leading diagonals. When these brackets are simplified, you would get minus 72 minus 89 And when you have two minus signs, they become a positive sign. It's minus 72 plus 89, and that is equal to 17. So we want to find dy now, right? So to find dy, we replace the variables of y with the constants, and the constants are 3, minus 5, 6, and we write back the third column as normal, and we mirror the first two columns. And we proceed to find the determinant as normal. When simplified, that will be equal to 10 plus 9 plus 24 is 43, minus 20 plus 18 minus 6 is equal to minus 8. Right? You see the occurrence of two minus signs, which will result in that being 43 plus 8, which is equal to 51. So the determinant of y, dy, is equal to 51. And you're going to replace the z column with the constants. Right, and you're going to mirror the first two columns. And we're going to solve the determinants normal. When simplified, minus 24 plus 10 plus 9 is minus 5, right? Minus 12 minus 15 minus 12, which is minus 39. We have a minus sign outside, so that makes it a positive sign. Plus 39. And we know that Daisy is found to be positive 34. Right, so if we recall, D was equal to 17, the X was equal to 17, the Y was equal to 51, and the Z was equal to 34. And we know X is equal to dx on D, which is equal to 17 on 17. Therefore, x is equal to 1. We know y is equal to dy on D, which is equal to 51 on 17, which is equal to 3. And we know z is equal to dz on D, which is equal to 34 on 17, which is equal to 2. So hence, the solution, x is equal to 1, y is equal to 3, and z is equal to 2.